century Europe, when two men, Isaac Newton and Gottfried Leibniz, were working on an idea that's been described as one of the greatest achievements of mankind. And boy, did they squabble over it. In this brief history, I want to reveal the personalities behind the calculations and show how mathematics drives science forward. 4 centuries ago, Galileo Galilei declared,
"The universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible to comprehend a single word. Without these, one is wandering about in a dark labyrinth."
Mathematics is the light that leads scientists out of the dark labyrinth of misunderstanding. Sure, telescopes and microscopes, observations and experiments have a role to play, but I believe mathematics is the driving force behind modern science. We celebrate the scientific genius of Albert Einstein, but what about the pioneering mathematicians on whose shoulders he undoubtedly stood? Particle physicists today are deeply indebted to a mathematician who was killed in a duel just after the French Revolution. And the mathematics of a Napoleonic soldier is the reason that you can hear me now. I should probably declare an interest at this point. I'm a mathematician, and in my view, mathematics is the language of the universe. Mathematics is the queen of science.
A brief history of mathematics with Marcus de Sautoy.
In Europe, in the late 17th century, where this brief history of mathematics begins, two exceptional mathematicians, one pure, Gottfried Leibniz, and the other more applied, Isaac Newton, were working on the same problem at the same time. Sir Isaac Newton, that great hero of British science, was described in an early school report as being
inattentive and idle.
Still, he went on to study at Cambridge, and in his early 20s started work on a new mathematics, the mathematics of moving things, or calculus. He described this new mathematics to friends, but didn't publish any account of how he did it, a decision that was to have ugly consequences. For at the same time as Newton was busy with his calculus, the young German scholar Gottfried Leibniz came up with a different version of the same thing. Now, whatever you thought of calculus at school, I'm here to try and make it clear. Bottom line, the calculus is a way of describing things that change. Take the famous apple that legend has it fell from the tree onto the young Newton's head and inspired his theory of gravity. At any particular point in time, how fast is the apple falling? The speed of the apple I just dropped is constantly increasing as gravity pulls it to the ground. So, how can you calculate what the speed is at any given instant of time? For example, after 1 second, how fast is the apple falling? What about after 2 seconds? Speed is the distance travelled divided by the time elapsed. So I could record the distance the apple drops in the next second, and that will give me an average speed over that period. But I want the precise speed at a precise moment, like now. Well, I could record the distance travelled over a shorter period of time, say half a second or a quarter of a second. The smaller the interval of time, the more accurate my calculation of its speed. But ultimately, to work out the precise speed at a precise moment of time, I need to take an interval of time that is infinitesimally small. But then I'm faced with calculating 0 divided by 0. The calculus makes sense of this seemingly impossible calculation. It tells you what the speed of something is tending towards as you make the time interval smaller and smaller. Calculus is the mathematics of things on the move. In mid-17th century Europe, this new mathematics moving things was something that both Newton in England and Leibniz in Germany understood. understood. In July 1676, Leibniz, who was travelling round Europe, received a letter from Newton. Newton had sent the letter to Henry Oldenburg, the first secretary of the Royal Society, who'd sent it on to Leibniz. In it, Newton described his version of the calculus. But he didn't share any of the crucial details about how it worked. Instead, he converted them into a curious code.
The foundations of these operations is evident enough, in fact. But because I cannot proceed with the explanation of it now, I have preferred to conceal it thus. 6ACCDAE 13EFF 7I319N 404QRR 4S8T 12VX.
Newton wanted to stake his claim on the calculus without giving away any of the details. But Leibniz didn't need the details. He understood. He dashed off an immediate and enthusiastic response, expressing admiration for what Newton had told him and presenting some discoveries of his own. Newton's letter, however, had taken 6 months to reach Leibniz. Henry Oldenburg had not been sure where to post it, given Leibniz's peripatetic existence, and when 6 months on Newton got a response from Leibniz, he didn't reply. It could have been the beginning of a fruitful exchange of ideas, but it wasn't, and the correspondence ended. Leibniz, meanwhile, set about recording his discovery of the calculus, working on it off and on for almost a decade. When he published it in 1684, the Bernoulli dynasty, a powerful family of Swiss mathematicians, took his ideas and broadcast them widely through the mathematical world. Leibniz began to receive credit for this powerful new mathematics. Newton didn't like it. Newton, by this time, was well established as a great scientist. Aged just 27, he'd been awarded the highly prestigious Lucasian Chair for Mathematics in Cambridge. He'd published countless hugely important scientific papers, including his laws of motion and the famous universal theory of gravitation. He went on to become an MP and was appointed Master of the Royal Mint. By the beginning of the 18th century, Newton was in a position of power.
I do not love to be dunned and teased by foreigners about mathematical things.
By which I think he meant, I do not like people giving Leibniz credit for the calculus, not me. 20 years after their aborted correspondence, rather than crediting Leibniz with having insights of his own into the calculus, Newton decided that Leibniz had stolen his ideas and spent 6 months working on them before replying to him. In 1704, Newton finally published his account of the calculus as an appendix to his book on optics. In it, he added a comment that implied that Leibniz had copied his work.
Some years ago I lent out a manuscript containing theorems about the calculus, and having since met with some things copied out of it, I have on this occasion made it public.
So began a campaign by Newton to claim that, while Leibniz may have published before him, it was he, Newton, who invented the calculus. For Newton, there was no question of sharing the credit. Leibniz, on the other hand, believed,
It is not a quarrel between Mr. Newton and myself, but between Germany and England.
In 1714, after years of acrimony and accusation, the Royal Society in London was asked to adjudicate between the rival claims. Was Newton the first to discover the calculus with his method of fluxions? Or was the credit due to Leibniz with his invention of the differential method?
The differential method is one and the same with the method of fluxions, excepting the name and mode of notation, and therefore we take the proper question to be not who invented this or that method, but who was the first inventor of the method. For which reason we reckon Mr. Newton the first inventor.
Leibniz, who published 2 decades before Newton, was nevertheless accused of plagiarism, and Newton was honoured with the discovery of the calculus. But the Royal Society's report was probably not the most impartial. The report was written by Sir Isaac Newton. When Newton died in 1727, he was given a state funeral and buried in Westminster Abbey with honours normally reserved for a general. Leibniz's memorial, by contrast, is a simple plaque erected in a small church in Hanover. But It is Leibniz's account of the calculus which eventually triumphs, not Newton's. Leibniz was lucky enough to have the backing of the influential Bernoulli family. The Bernoulli family became Leibniz's disciples, taking his mathematical messages, clarifying them, realizing their deep implications, and spreading the word across Europe. In particular, the Bernoullis realized just how powerful Leibniz's calculus was for finding the best solution to all manner of problems. This is the real power of the calculus, its ability to home in on the most efficient solution. It's this that makes it one of the most important tools in modern science. The natural world is in a constant state of flux. So many things are on the move, and if you want to understand and predict such things, calculus is invaluable. Designers use it to optimize construction. Engineers exploit it to minimize energy use or maximize the speed of planes, trains, and automobiles. Space travel depends on it.
The basic rocket equation, which tells how rockets work, uses the calculus.
Astronaut Jeff Hoffman. But does he ever think about Newton and his calculus when he's out there in space?
I have to admit that there are so many other things to do that I really wasn't thinking that much about the history of science as we were approaching the Hubble Space Telescope, getting to reach out with the mechanical arm and grab it. There's lots of other things on your mind. But it's nice to know that Newton is safely ensconced in the computer and that his mathematics is guiding us on our path to a successful mission. You know, space travel without Newton and his calculus would just be inconceivable.
Calculus is one of the linchpins of our modern technological world. The calculus underpins our understanding of so many things: mechanics, electricity, magnetism, the solar system. I could go on and on. It's a stunning mathematical insight that's had a profound, wide-reaching and long-lasting impact on science. And it's not just in the world of science that it's found a use. Every day, across the industrial and financial world, investors use the calculus that Newton and Leibniz started to maximize profits. Matthew Killier is a quantitative analyst for a hedge fund.
The kind of scientific hedge funds at the time we're trying to use mathematical modelling to help predict the world's financial markets, to make bets in the world's financial markets. It's quite staggering to step back and realise that every day you're entrusting $13 billion to a computer which is using mathematical models and code which are crucially underpinned by the ideas and equations from calculus, an idea that was formalised over 300 years ago.
To say calculus is one of the greatest achievements of mankind is, I think, entirely justified. And it's the calculus of Leibniz, not Newton, that proved to be the most powerful. As a pure mathematician myself, I have to say it pleases me that it was the pure mathematics of the humble Leibniz, rather than the more applied approach of the more scientifically minded Newton, that eventually triumphs. But with the benefit of hindsight, it's clear that both men's analysis left a lot to be desired. Tomorrow we'll meet the man who stood on Newton and Leibniz's shoulders and realised the true power of the calculus. Thanks for listening to